Hello everyone, welcome to Q Physics Academy. In previous 3 lectures, we are basically discuss about the Coulomb's law, and in the next lecture, basically lecture number 10. In lecture number 10, we are discuss about the applications of Coulomb's law. Okay. Now, in today's lecture, we are discuss about very important applications of Coulomb's law. And this is in this applications we are basically discuss how to find out the frequency of oscillation of a charged particles. Okay, frequency of oscillations of a charged particle हम लोग फाइंड करने वाले हैं. ठीक है. सो फ्रीक्वेंसी ऑफ ऑसिलेटर हम लोग पिछले वाले लेक्चर में बेसिकली अनस्टेबल इक्विलिब्रियम और स्टेबल इक्विलिब्रियम के बारे में डिस्कशन किया था. स्टेबल इक्विलिब्रियम आपको कब मिलता है? जब when a negative charge it oscillate in between negative charge, and when a positive charge it oscillate between two positive charge, then we get stable equilibrium. But when a negative charge it oscillate between a positive charge, basically this is a negative charge, and here another negative charge it oscillate in between negative charge. Another case there is positive charge and also positive charge, and here also a positive charge which oscillate in between two positive charge. That two case give us stable equilibrium. Okay, that means here the negative charge or positive charge is in stable equilibrium. Okay, stable equilibrium. That means this charge reach stable equilibrium. Another case, it's when a negative charge is oscillate in between a positive charge, then in that case for negative charge in unstable equilibrium. So charge will be in unstable equilibrium. Unstable equilibrium. Okay. Now using this concept, using these two concepts, stable equilibrium or unstable equilibriums, we are now find out the frequency of oscillations. Basically, for frequency stable equilibriums means in that case particle in stable equilibriums, particle are basically oscillate in simple harmonic motions. Basically, in stable equilibrium, particle oscillate in SHM motion. But in unstable equilibriums, particles are not oscillate in SHM motion. So when particles are oscillate in particles are reach in stable equilibrium, that means the particle motions is simple harmonic motions. Then we apply all the properties, all the mathematical approach of simple harmonic motions. Okay. So first of all, here question is basically this is the configuration. Okay, this is the configurations, and this is the x-axis, and this is the y-axis. Okay, y-axis, and at origins, okay, at origins there is present a charge plus q charge, and this is the locations O, and at positions A, and the coordinate of the A is basically A comma 0. There also another position, this coordinate is very A minus 0, and there have also positive charge plus Q. Okay, this is the configuration. Okay, now we displace this charge at O at a small distance, x along the direction A. Now the charge is located is here, and this distance is x. Distance is basically x. Now charge is basically here. So as you know, as we displace this positive charge at this, then the particle will be oscillate in like a simple harmonic motion. So this simple harmonic oscillations, as we find out the frequency of oscillation of the charge. To find out, question is basically for this displacement, find out the oscillation frequency of charge. Find the oscillation frequency of charge Q. Find the oscillation frequency of charge Q at. So this is the concept. So now, as a positive charge is oscillate in between two positive charge, that means the positive charge is reaches to stable equilibrium point. Okay, so this charge particles are oscillate as like a simple harmonic motions. So as the particles are oscillate in simple harmonic motion, according to SHM, okay, so particle have a restoring force is proportional to x, and it is equals to basically kx, and where k is equals to m omega square. Okay, k is basically m omega square, and omega is equals to k upon m, and omega is the angular frequency. Okay, and m is basically mass, where m is mass of charge Q atom, and omega is the angular frequency. Angular frequency of oscillation. Okay, angular frequency of oscillations. It's okay. Now we're trying to find out what is the net resulting force on charge Q when the charge is located at a position T. This is the position D. So now assume now charge Q is now located at position D at a distance x from origins, at a distance x from origins. Okay, so now that case, this is the origins O. Now the charge is located at a distance D, and this is the point A, positions A, and this is the positions B. And now distance between O and B is also A, and also the distance between O and A is also A. And now the distance between O and D is equals to x. Okay, so finally is nothing but A plus x, and distance between B and A is nothing but A minus x. Okay, so now Here the basically present plus Q charge. Here the present plus Q charge. Here also present plus Q charge. Okay. So now find out the force on this charge by this Q charge. Okay. So now in that case, the force. Now in that case, force acting on one plus Q charge at D. It's denoted by now force acting on charge Q at D. Charge Q at D by charge Q at A. Okay, at A. At A. And it is equals to, this is the first case, and it is equals to basically if D vector it's equals to, if D it's equals to 1 upon 4 pi epsilon naught Q square A minus square 4. Okay, because there is a force. Why negative? Because directions. Okay, negative x directions. Now another case, at by force by charge Q at A that is equals to D, it's equals to 1 upon 4 pi epsilon naught into Q square plus x square. That is also the answer in its direction. Now, on charge Q at D. Okay, if vector equals to if D plus if, because these two charges are along a straight lines acting, because this two force acting along a same line, acting along a same line. Okay, acting along a same line. So now the overall the net force acting on this charge, it is equals to basically a force, it is equals to 1 upon 4 pi epsilon naught Q square A plus x whole square plus x cap plus 1 upon 4 pi epsilon naught Q square upon A minus x whole square minus x square. Okay, minus x square. So now the magnitude of this force, it is equals to basically 1 upon 4 pi epsilon naught Q square upon A plus x whole square minus 1 upon 4 pi epsilon naught Q square upon A minus x whole square. So we take a common Q square upon 4 pi epsilon naught, it is equals to 1 upon A plus x whole square minus a minus x whole square. Okay, a minus x whole square. Now simplify this expression. Okay, now simplify this expression. So resulting force F vector equals to q square upon 4 pi epsilon naught equals to basically in denominator a plus x whole square, a minus x whole square, and first term is a plus x. So basically a minus x whole square minus a plus x whole square. Now take negative sign common, so it is equals to minus q square upon 4 pi epsilon naught. It is equals to a plus x whole square minus a minus x whole square upon a square minus x square whole to the power square. Okay, x square minus x square whole to the power 4. Now in numerator, it is the expression is like minus q square upon 4 pi epsilon naught, and it is equals to basically 4ab, 4ax, okay, upon 4ax upon a square minus a square. So overall, this is the expressions of resulting force. So the magnitude of this resulting force, it is equals to basically q square upon 4 pi epsilon naught 4ax upon a square minus x square whole upon x square. Now we apply this approximation. As the displacement of this charged particle is very small, so here, so when approximation is basically x is very less than x, because displacement of this charged particle is very small. So x is very small compared to the distance of the charge at point A and B from origin. Okay. So as we use these approximations, resulting force vector is equal to q square upon no neglect. So overall it is equals to 4. So the final result is basically minus, there is a minus sign also, minus sign, minus q square x upon pi epsilon 0 aq. So this is the magnitude of the resulting force on charge q. Okay, so this is the equation 2. This is the equation 2. Now comparing equation 1 and 2, and equation 1 is basically resulting force is equals to kx. This is the equation 1. Now equating equation 1, comparing equations 1 and 2, we get the results. It's equals to minus q square so basically comparing equation 1 and 2, 1 and 2, we get k is equals to basically q square upon pi epsilon 0 aq. Okay, pi epsilon 0 aq. Pi is nothing omega square. Q is nothing equals to basically epsilon aq, pi epsilon 0 aq. So omega square is nothing but q square upon m pi epsilon 0 aq. So omega is nothing but q square upon m pi epsilon 0 aq. Omega is not 2 pi n or 2 pi f. This is the linear frequency. So 2 pi f is equals to q square upon m pi epsilon 0 a cube. So f is nothing but 1 upon 2 pi root under q square upon m pi epsilon 0 q. So this is the expressions of frequency. Okay, this is the expressions of frequency. So now simplify these expressions. So this is the frequency of presence of charged particles. When a positive charge is initially placed in between two positive charge, and that positive charge will basically oscillate. But I mean displaced from its mean position at a small distance, then it will perform simple harmonic motions, and due to for simple harmonic motions, particle have some linear frequency and also angular frequency. And what is the expression of linear frequency? This is the expression of frequency and all cases. So from these expressions, so expressions is nothing but q upon 2 pi 1 upon m pi epsilon 0 a cube. So the frequency of oscillations is from these expressions we get find out some important note. We are find out some important note. Frequency is directly proportional to q. It means is q at d. Q at d. Okay, q at d. This is the expression q at d. If we increase the magnitude of this charge of this magnitude of the charge of this charge, magnitude value of the charge, amount of charge, increase the q. So f is inversely proportional to 1 upon root m. Okay, 1 upon root m. Okay, 1 upon root m. Okay, fine. So m is the charge of q, which is basically located at d. So if we increase the mass of this charge, then frequency decrease. If we increase the charge of this charge, then frequency increase. So these two approximations are very important. These two mathematical concepts are very important. So basically, this is the configuration. There are a positive charge. This is also valid for negative charge, also positive charge, and at mean positions, O, there are a charge Q. And this charge is now displaced a small distance, either A or either B, either positive x-axis or either negative x-axis, arbitrary direction. So for this displacement, this charge is performed simple harmonic motion. And for this simple harmonic motion, this charge particle have some linear frequency, and that frequency f is directly proportional to q and also inversely proportional to root m. Okay, inversely proportional to root m. So this is the concept. These two concepts are very important. Using these two concepts, we are find out many problems also in electrostatics. Okay, so this is the applications of Coulomb's law. We can use this Coulomb's law application, and using this Coulomb's law applications, we are find out the frequency of oscillations and how this frequency depend on q and mass of the charged particles. Fine. So this is the basic expressions. So okay, fine. Now we get another concept, that is electric field. Okay, electric field. So how can I find out electric field, as well as some basic properties or some basic phenomena we are described here. Okay. Now we find out the electric field expressions. What is electric field? Okay. Electric field. Electric field. Electric field. Let us consider. Okay. Let us consider. We have a several point charge. Several point charge. We have considered several point charge at a particular location. There have some several point charge. Several point charge. That is Q1. That is Q2. And it is also Qn. Several point charge at a distance R1, R2, Rn. So we can assume the coordinate system, that is the x-axis, that is the y-axis, that is z-axis. From this coordinate, the distance of Q1 is R1, distance of Q2 is R2, and distance of Qn is basically Rn. ओके थोड़ा सा इस प्रॉब्लम को हम लोग और भी इजी में हम लोग इसको हम लोग थोड़ा सा इजी वे में डिस्कस कर लेते हैं इलेक्ट्रिक फील्ड so consider some point charge is present here. Some point charge. Let us consider some point charge present here. So this is the Q1, this is the Q2, and this is the Qn, and also. And consider this is a source charge. These all are basically source charge, and this is test charge. These all source charge are basically stationary, and test charge is maybe moving. Now, distance between source charge and test charge is basically Q1 से लेके Q तक का distance basically R1 है, R2 से लेके इसका distance basically R2 है, Qn से लेके इसका distance basically Rn. So this is the, we are assume that. Now the total force on Q, we are now find out the total force on Q. Okay, so total force on Q capital Q, total force on capital Q, each F vector it's equals to F1 vector, F2 vector, F3 vector, and so on. Okay, and so on. So now we take 1 upon 4 pi epsilon naught is common. So 1 upon 4 pi epsilon naught common. So expression is Q into Q1 upon R1 square and express R1 cap. Okay. Second is basically Q2 into Q upon R2 square into R2 cap plus and so on. Okay. So we take a common also Q part, capital Q. So the expression is Q upon 4 pi epsilon naught Q1 R1 square R1 cap plus Q2 R2 square R2 cap and so on. So now we can again simplify this expression in summation forms. So it is equals to basically Q upon 4 pi epsilon naught to summation over I1 to N, okay, Qi upon Ri square Ri cap. So it can be expressed Q into 1 upon 4 pi epsilon naught summation over I1 to N Qi upon Ri square Ri cap. So this can be expressed, this term can be expressed as an electric field. So Q into E. This term can be expressed as electric field. So E is called electric field. So where E is basically 1 upon. So we can always get electric field by source charge, not test charge. So electric field on test charge by the source charge is, so basically this expression is something like I 1 to N Qi upon Ri square Ri cap. So this is called electric field. So finally this is the electric field of source charge in number of source charge. This is equals to 1 upon 4 pi epsilon naught I1 to N Qi upon Ri square Ri cap. So this is the expressions of electric field of the source charge. So we always get electric field for only source charge on test charge. Okay, on test charge. Fine. So this is the E is called the electric field of the source charge on test charge Q, on test charge Q. So for single point charge, expressions of the electric field is equals to 1 upon 4 pi epsilon naught Q upon R square. So for single point charge, okay, so for point charge, electric field expressions is nothing but 1 upon 4 pi epsilon naught Q upon R square at a arbitrary, R is basically at a arbitrary distance, and where we find out the electric field. R is nothing but where we are trying to find out, we are interested basically, to find electric field. Okay, electric field. If capital Q charge is basically present at that distance, at a R distance, then we find out the electric field on plus Q charge. So this is the expression. Okay, that's fine. So this is the electric field for single point charge, and this is the expressions of electric field for a source charge. Number of source charge. So physical significance. What is the physical significance of electric field? Physical meaning of electric field. What is the physical meaning of electric field? Let's take a heading. Physical meaning of electric field. Physical meaning of electric field. What is the physical meaning of electric field? Electric field is a vector quantity. Okay, it's always true. and that varies from point to point. As the electric field expression is for point charge is 1 upon 4 pi epsilon naught upon r square r cap. So it's mean electric field is a vector quantity, and this field is vary from point to point, and it is determined by the configuration of source charge. Source charge configuration is very important. Source charge configuration. इस चार्ज कॉन्फ़िगरेशन मींस जो सोर्स चार्ज के बारे में जो सोर्स चार्ज के लिए आप फाइंड करना चाहते हैं इलेक्ट्रिक फील्ड, दिस सोर्स चार्ज स्फेरिकली सिमेट्रिक और cylindrically symmetric or point charge. That is very important. There is a line charge and there is a spherical charge density or there is a cylindrical charge density. So charge configurations is very important. So what is it's a vector quantity and it is very point to point, and it is determined by the configuration of point or source charge. Okay, source charge ka configuration is very important to find out the electric field. It's okay. Also physically जो इलेक्ट्रिक फील्ड है ना इज द फोर्स, इट इज इलेक्ट्रिक फील्ड इज फोर्स पर यूनिट चार्ज बेसिकली. अब देखिए वी आर फाइंड आउट फोर्स ऑन दिस कैपिटल Q इज बेसिकली Q into E. E is basically source charge due to source charge. So E equals to basically F upon Q. So what is the meaning of this physical electric field? Is a definition is physically force per unit charge, which charge basically test charge, force per unit test charge, force per unit test charge, that would be external at test charge, would be external force per unit charge that would be extracted on the test charge, that is the called electric field. Okay, so what is the physical meaning? So first physical meaning, it is vector quantity, of course vector quantity, it is vector quantity. Okay, second physical meaning, it varies from point to point, it is varies from point to point, point to point. Third, it is determined, electric field is determined by the configuration of source charge, by the, it is very important. Source charge, okay, by the configuration of source charge, by the configuration of source charge. And also physically electric field means fourth point, physically E of R is the force per unit charge, force per unit charge, and that force would be extracted on this test. Okay, so physically E is the force per unit charge. Okay, electric field means force per unit charge, and that force exerted, not exerted, force is exerted on the test charge. It is very important, on the test charge. Okay, so electric field means force per unit charge, and that force is exerted on capital Q, and it is actually equals to that. So force on test charge is, and here basically F is the force on test charge. by source charge. It is expressed in f of q. Q is basically charge of test charge. Charge of test charge and E is the electric field due to source charge. Clear? Due to source charge. Okay, fine. This is the expressions, physical meaning of these expressions. Okay. Now we can find out the electric field expressions also, and what is the expressions of electric field and physical meaning of this electric field. We are find out. Okay. Now we're trying to find out the electric field calculations above the midpoint between two equal charge at a q at a distance d apart. Okay. So please take a heading. Electric field calculations electric field calculations at a distance z above the midpoint between two equal charge. Okay. Two equal charge q at a distance d apart. Okay. Here is basically two equal charge are at a distance d apart, and from the midpoint at a distance z above the midpoint. Okay, above the midpoint, find out the electric field. So this is our problem. Please take a heading. This is very important. We have described the mathematical approach, and also so for competitive exam purpose, you can assume only the formula and corresponding approximations formula also. Okay, but here I describe all the properties, mathematical approach, what are the how can we find out the electric field, all are we are discussed here. Okay, so this is the pictorial representation. This is the q and this is also q, and this is the midpoint. Okay, and the distance between these two particles, these two charges is basically d, and this is also d by 2, this is also d by 2, and from the midpoint, above the midpoint at a particular distance z at a point p, we are trying to find out the electric field. Okay, so at p we are find out the electric field also. So this is the configurations. So as you know, from charge q a, this is the a positions, this is the b positions. Okay, for charge at a we are find out electric field at p, and that's a bit directions is as like it. Okay, this is the electric field u1. We are assuming this is the electric field u1. Okay, and also the charge q at point b, for this charge we are get another electric field, and this is the electric field e2. So this is the electric field E2. Okay, the electric field E2, and the resultant electric field, its direction is along this direction. This is the resultant electric field direction, and this is calculate E. Okay, so E1 here, E1, the field of the left charge alone, field of left charge. Okay, E2 is the field of right charge. Field of right charge. Okay, fine. From the figure configurations, the horizontal component, it cancel each other. So for this electric field, this is the horizontal component and this is the horizontal component. So the horizontal component cancel each other. On the other end, vertical component are basically conspire. That means add each other. So here the horizontal component are cancel each other, and other vertical components are basically conspire. So we can draw the point P only. So this is the direction of E1. This is the direction of E2. E1, E2, and this is the resultant of electric field. Okay, and this electric field E1 have a component, vertical component along these directions, horizontal component along these directions. Okay, and also for E2, vertical component have along these directions, and a horizontal component it along these directions. Okay, so this is the angle theta. This is the angle theta. So okay, these two component are basically cancel each other, but these two component are basically at conspire. Okay, these two component are at, and this horizontal component are cancel each other. So horizontal component cancel, each other. Horizontal component cancel each other, but vertical component add each other. Okay, fine. And all the vertical component are in the direction of Z directions. So Ez, it equals to basically, Ez is basically 2 into E1 or E2, arbitrary, both have a same magnitude. Okay, so E1 cos theta, where E1 is basically 1 upon 4 pi epsilon naught Q1 upon R square. So R is the basically this the point. This is the R. Okay, so U1 is basically that. So substitute here. So 2 into 1 upon 4 pi epsilon naught Q upon R square cos theta. So from the given configurations, here R is nothing but for the given configurations, R is nothing but basically Z square d by t whole square. Okay, that's fine according to Pythagoras law. And also cos theta, from the given configurations, cos theta is nothing but Z upon R. Cos theta is upon Z upon R. From the given, if we take this triangle, so from this triangle cos theta is nothing but Z upon R. Okay. So cos theta is nothing but Z upon R. So if we substitute all the value, so the magnitude of the field Z is basically E. It is equals to E equals to Z. Z equals to 2 upon 4 pi epsilon naught Q upon R square, and R square is nothing but R square, okay, Q upon R square. Cos theta is nothing but Z upon R. Z upon R, and it is the direction is along Z cap. Along Z cap. Okay, along the Z cap from the configurations. Okay, fine. So finally, the resultant electric field is E equals to 1 upon 4 pi epsilon naught 2qz upon R cube Z cap. So it is equals to basically 1 upon 4 pi epsilon naught 2qz upon R cube. R cube is nothing but Z square plus D by 2 whole square 4 upon 3 Z cap. So this is the expressions of electric field for the overall system. So please remember. So please remember. So electric field for two equal charge, and these two equal charges are basically at a distance apart D, and we are trying to find out the electric field above the midpoint at a distance Z. Okay. So the electric field expression is basically 1 upon 4 pi epsilon naught 2qz upon Z square upon D by 2 whole square all upon 3 Z cap. Now we use the approximations. If we take here approximation, this approximation is very important for competitive exam purpose. So approximation, case approximation, this approximation is very important. Approximation is here. So when Z value, further basically we are find out the electric field is very large compared to D, distance between two particles. Then what happened? Then basically using these approximations, the electric field is basically 1 upon 4 pi epsilon naught 2qz upon Z square plus D square upon 4 whole to the power 3 Z cap. But here Z is very large compared to D by 2. So as D is a small quantity, so D is small, so D square is also small, very small. D square is very small. So we can neglect this term. Okay, Z is a large quantity and we can find out the square. So it's also very large, and D is very small quantity and it's square. So it's also very small. So large plus small, that means we get also large quantity. So it is using this approximations we get 1 upon 4 pi epsilon naught 2qz upon Z cube Z cap. So it is equals to basically 1 upon 4 pi epsilon naught 2q upon Z square Z cap. So finally we get at a large distance from the charge distributions, at a large distance, where find out the electric field is equals to 1 upon 4 pi epsilon naught 2q upon Z square into Z cap. Okay, so it's give us another statement. So when Z is very large compared to D, then the system became like a point charge. Okay, so when Z is very large compared to D, then system. Okay, then system behave like a point charge. Behave like a point charge, and total value of the charge is basically 2q. So the electric field behave like a point charge, and that case electric field basically 1 upon 4 pi epsilon naught 2q upon z square. So this is the conditions. So आपके पास एक two electric charge है, and these two electric charge are basically separated from each other at a distance d apart, and we are trying to find out the electric field above the midpoint at a distance z. And the electric field expression is 1 upon 4 pi epsilon naught 2qz upon z square plus d by 2 whole square upon 3 by 2 z cap along the z direction. Okay. If the z distance is very large from the axis of this charge, then these two charge are behave like a point charge, and the system have a total, and then we are find out the electric field for 2q charge, 2q point charge. Okay, so please remember the concept. It is very important. Using this concept, we can find out the also very problem in the directions. Okay. 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 ओके ठीक है. सो आज का क्लास हम लोग आज का जो क्लास है बेसिकली this class is stop is here. This class is now stop here. In the next class we are basically discuss the continuous charge distribution. What is the charge distributions, and we have find out the electric field for a line charge density, and then we find out the electric field line, and also another concept, electric flux, as well as the various concepts. Okay. Okay. So this is a very important concept. So this important concept are very important. This is the basically please take a note and remember the line. This is the configuration QQ, and the separation is basically D, and at a midpoint to at a distance Z, we are finding out the electric field, and that electric field is basically 1 upon 4 pi epsilon naught 2z upon z upon z square upon d by 2 whole square upon 2 z square. But if we approximation is very large compared to D, this system like a point charge, and the total charge of the system is 2q, and then electric field is equals to 1 upon 4 pi epsilon naught. So please remember. So please remember the concept. Okay. So this two, take a note. This is very important for competitive exam purpose. These two are very important for competitive exam purpose. So we can in the next class, using these expressions, we take a problem and what is the applications of this problem, and also we have discussed the charge distributions, that is continuous charge distributions, line charge distributions, surface charge distributions, volume charge distributions, and so on. Okay, thank you.